Chapter 5, Force. This lecture will help you understand the law of action and reaction and total forces in one dimension. We now want to define the difference between forces and interactions. A force is simply a push or a pull, while an interaction is something that occurs between one thing and another. As an example, when you push against the wall, you're interacting with the wall. Newton's third law of motion is known as the law of action and reaction. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. For example, when your hand presses on the wall simultaneously presses on your hand. Your hand and the wall press on each other with equal and opposite forces. When a hammer hits a nail, it exerts a force on the nail. At the same time, the nail exerts a backward force on the hammer. If you don't believe it, imagine hitting the nail with a glass hammer. If the force of the nail and the hammer, that would cause the glass to shatter. When a bat hits a ball, the ball exerts a force on the bat. When you pull something with a rope in a tug of war, that person pulls back on you. When your chair pushes up on you, the normal force, you push down on the chair. All forces come in pairs, called action-reaction pairs. These forces occur simultaneously, and we can't say which is the action and which is the reaction. When describing Newton's third law of motion, we speak of an action and reaction forces. One force is called the action force, and the other force is called the reaction force. The forces are really copairs of a single interaction. It is not possible for either force to exist without the other. The action-reaction pairs are always equal in strength and opposite in the direction of motion. Most importantly, the two forces always act on different objects. Watch the video of the fan cart seen on Blackboard. A soccer player kicks a ball with 1,500 newtons of force. The ball exerts a reaction force against the player's foot of A, somewhat less than 1,500 newtons, B, 1,500 newtons, C, somewhat more than 1,500 newtons, or D, none of the above. The answer is B, 1,500 newtons. This is the meaning of Newton's third law. The force of the kick is equal to the force of the ball on the foot. These are some examples of action-reaction pairs. The action, an object A exerts a force on object B, and the reaction, object B exerts a force on object A. The action is the tire pushing on the road. The reaction is the road pushing on the tire, propelling the car forward. The action is the rocket pushing on gas, and the reaction is the gas pushing on the rocket. The action is the man pulls on a string, and the reaction is the string pulls on a man. The action is the earth pulling on a ball as it falls, and their reaction is the ball pulls on the earth. Sometimes it is not so easy to decide which is the action and which is the reaction. In truth, it doesn't really matter. You can easily call one the action and the other the reaction without affecting the final answer. To make this simpler, we will use the notation F of A on B, which is the force of A on B, and we will use F of B on A, which is the force of B on A. Either can be called the action and the other the reaction. Since the action-reaction pairs are equal and opposite, we simply write F of A on B is equal to the negative of F of B on A. The minus sign again indicates the direction of the force. If one force points to the right, the other force points to the left. If object A exerts a force on object B, then object B exerts a force on object A. The pair of forces as shown is called an action-reaction pair. The interaction occurs at the contact point between the two objects. The forces of equal magnitude point in opposite directions. The force from B to A points to the left, and the force from A to B points to the right. When you step off a curb, Earth pulls you downward. The reaction to this force is a slight air resistance, non-existent in this case. You pull the Earth upward, none of the above. C. You pull the Earth upward. We need to mention consequences. When you step off the curb, you may fall several inches, but the Earth is pulled up by you only a fraction of the width of a proton. The Earth does move, but it is imperceptible. Since the action and reaction pairs always are applied to different objects, the two objects may not have the same mass. This means that the consequences are different for the two objects. The object with the greater mass will have a smaller acceleration. The object with the smaller mass will have a larger acceleration. Consider the propulsion of a fish through the water. A fish uses its fins to push water backwards. In turn, the water reacts by pushing the fish forwards, propelling the fish through the water. The size of the force on the water equals the size of the force on the fish. The direction of the force on the water backwards is opposite the direction of the force on the fish forwards. Flying gracefully through the air, birds depend on Newton's third law of motion. As the birds push down on the air with their wings, the air pushes their wings up and gives them lift. When a cannon is fired, the acceleration of the cannon and the cannonball are different because the A, forces don't occur at the same time, B, forces, although theoretically are the same, in practice aren't the same, C, the masses are different, or D, ratio force to mass are the same. C, masses are different. Consider a high-speed bus colliding head-on with an innocent bug. The force of impact splatters the unfortunate bug over the windshield. Which is greater, the force on the bug or the force on the bus? A, the bug, B, the bus, C, both are the same, or D, cannot say. Answer is C, both are the same. Although the forces are equal in magnitude, the effects are very different. Do you know why? Two people of equal mass on slippery ice push off from each other. Will both move at the same speed in opposite directions? A, yes. B, yes, but only if both push equally. C, no. Or D, no, unless acceleration occurs. Answer is A, yes. However they push, the result is equal magnitude forces on equal masses, which produces equal acceleration and therefore equal changes in speed. When lift equals the weight of a helicopter, the helicopter A, climbs down, B, climbs up, C, hovers in midair, D, none of the above. C, hovers in midair. The net force acting on the helicopter is 0. When lift is greater, the helicopter A, climbs down, B, climbs up, C, hovers in midair, D, none of the above. B, climbs up. We have two forces that are not equal. The upward lift is greater than the downward pull of gravity. We can also conclude that lift and gravity are not action-reaction pairs. Action-reaction pairs are always equal and opposite. A bird flies by A, flapping its wings, B, pushing air down so the air pushes it upward, C, hovering in midair, D, inhaling and exhaling air. B, pushing air down so the air pushes the bird upward. Slightly tilted wings of airplanes deflect A, oncoming air downward to produce lift, B, oncoming air upward to produce lift, C, both of these, D, neither of these. A, oncoming air downward to produce lift. When a wing diverts air downward, it exerts a downward force on the air. The air simultaneously exerts an upward force on the wing. The vertical component of this upward force is lift. The horizontal component is drag. Compared with a lightweight glider, a heavy glider would have to push A, downward with greater force, B, downward with the same force, C, downward with less force, D, none of the above. A, downward with greater force. The force on the air deflected downward must equal the weight of the glider. Watch the L1011 video on Blackboard. In particular, watch the motion of the smoke. For now, we will only deal with forces that are horizontal or vertical. When forces act in the same line, we can just add or subtract their magnitudes to find the net force. The 2 kilogram mass has 3 forces acting on it, 32 newtons and 10 newtons to the right and 15 newtons to the left. We call to the right positive and to the left negative. Add the 3 forces with signs to get a positive 27 newtons or 27 newtons to the right for the net force. We say that an object at rest is in static equilibrium. An object moving in a straight line at a constant speed is in dynamic equilibrium. In both types of equilibrium, there is no net force acting on the object. The net force is the vector sum of all the forces acting on an object. If the vector sum is not equal to 0, we say the net force is unbalanced and the object will accelerate, which includes changing direction.